Everyone, in this class we'll try to learn about membrane potential. The objectives would be to understand the concept of resting membrane potential, that is RMP, explain the mechanism of genesis and maintenance of resting membrane potential, give the normal values of resting membrane potential in different excitable tissue and equilibrium. An electrical potential difference exists across cell membrane of all living cells, with inside being negative in relation to the outside. This potential difference is called as membrane potential. Ions arrange themselves along the outer and inner surfaces of the cell membrane. At resting state of cell, the membrane potential is called as resting membrane potential. In a nerve cell, the resting membrane potential is minus 70 millivolts. When neuron is stimulated, membrane potential changes and inside of the cell becomes positive due to the depolarization. The membrane potential during this state of activation is called as action potential. RMP plays an important role in deciding the degree and duration of action potential, as the RMP is the level from where the phase of depolarization starts. Some tissues like visceral smooth muscles, RMP is not stable, that it keeps on fluctuating. This is resting membrane potential different excitable cells. In neuron it is minus 70 millivolts, skeletal muscles minus 90, and cardiac muscle it is 90 minus 90 millivolts. Membrane potential is mainly due to the distribution of ions across the cell membrane, which results mainly from the selective permeability of the cell membrane to various ions at rest. However, this is influenced by various forces acting on ion distribution. Understanding the following concepts of physics help in understanding the learning of resting membrane potential. The resting membrane potential depends on various factors like selective permeability of the cell membrane to various ions, depends on the Gibbs-Donnan equilibrium, Nernst equation, and Goodman's-Hodgkin's equation. The cell membrane is selectively permeable to ions and other solute particles. Some ions are highly permeable and some are less permeable and others are impermeable. The permeability mainly depends on the molecular weight and the radius of the ions in their hydrated form. Though the ions like sodium, potassium chloride, and bicarbonate are diffusible through the membrane, permeability is more for potassium. The permeability of potassium is 500 to 1000 times greater than that of sodium for its effective radius. The membrane is practically impermeable to intracellular proteins and organic phosphates. Gibbs-Donnan equilibrium. When two solutions containing ions are separated by a semi-permeable membrane, at equilibrium, each solution will be electrically neutral. The total quantity of cations will be equal to the total quantity of anions. Also, the product of diffusible ions on one side of the membrane will be equal to the product of diffusible ions on other side of the membrane. So this is called as Gibbs-Donnan membrane equilibrium. For example, two solutions A and B containing sodium and chloride ions are separated by a semi-permeable membrane. The concentration of sodium and chloride equals to the concentration of sodium and chloride in solution A and B. So that is number of anions and cations, they are equal to each other. So according to Gibbs-Donnan equilibrium, the solution should be electrically neutral, which means cations in A is equal to anions in A, and cations in B is equal to anions in B. So the product of diffusible ions on both sides will be equal, which means diffusible ions in A into diffusible anions in A is equal to diffusible cations in B into diffusible anions in B. So thus this Gibbs-Donan equilibrium gives this particular equation, and thus there will be equal and balanced distribution of ions at equilibrium. However, when non-diffusible ion X is added on one side, then as per Gibbs-Donan equilibrium principle, the distribution of diffusible ions will change to maintain the electroneutrality of the both the sides. When the substance X is added, which carrying negative charge is added to the solution A, which is non-diffusible, so then to make up for the equilibrium of the ions, so there will be more concentration of sodium and there will be less concentration of the chloride in solution A compared to the solution B. Whereas in solution B, so there will be less amount of sodium and more amount of chloride. So that's how, so when an, I mean, indivisible uh, cations when are added to the solution A, so there will be unequal distribution of anions and cations in solution A and B. So, so, so this is what I mean. Here it is saying that so whenever the presence of non-diffusible ion in one side of the membrane affects the distribution of other ions to which membrane is permeable. So this results in asymmetrical distribution of the ions across the cell membrane, and this is called as Gibbs-Donan effect. And this reaction shows the same thing. Nernst equation. In accordance to Gibbs-Donan equilibrium, asymmetrical distribution of diffusible ion occurs across the cell membrane with more cation present inside. Therefore, potassium will try to diffuse into ECF from ICF, which is opposed by electrical gradient created by presence of non-diffusible ions inside the cell. Thus, finally, equilibrium is reached between the concentration gradient and electrical gradient, resulting diffusion potential, that is equilibrium potential across the cell membrane. So the degree of this equilibrium potential is determined by the Nernst equation. That is, the equilibrium potential is equal to RT divided by ZF log of concentration inside, concentration outside that particular ion. Okay. So where the EM is equilibrium potential, R is a natural gas constant, T is absolute temperature, F is Faraday constant, okay, and Z is valency of ion. Ion is natural logarithm, and I is concentration ion inside the cell, and con O is concentration of ion outside the cell, that is extracellular fluid. At normal body temperature, converting from the natural log to the base of 10 log and replacing some constant with numerical values, the equation can be simplified as equilibrium potential is equal to plus or minus 61 log of concentration inside by concentration outside the cell. Thus, the Nernst equation helps in the calculating the equilibrium potential for each ion individually. Okay. So thus the concentration of ions in ECF and ECF and equilibrium potential for different ions is like this. For sodium, the ECF concentration is 150, the ICF concentration is 15, and the equilibrium potential is plus 40 plus 60 millivolts. Whereas for potassium, the ECF concentration is 5.5 moles per liter, and ICF concentration is 150, and the equilibrium potential is minus 90 millivolts. For chloride, it is 125, 90, and minus 70 millivolts, whereas for bicarbonate, the equilibrium potential is minus 25, and for calcium, the equilibrium potential is around plus 130 millivolts. Goldman Hodgkin's-Katz equation is the magnitude of membrane potential at any given time on the distribution of sodium, potassium chloride, and on the permeability of each of these ions. Okay, so the the resting membrane potential, it mainly depends on the equilibrium potential of sodium, potassium chloride, and it mainly depends on the permeability of these ions across the cell membrane. The role of different ions in generation of the membrane potential is accurately described by Goldman Hopkins equation, so it is called as Goldman's constant field. Okay, so it is nothing but it is the summation of the Nernst potential of the potassium, sodium, and the chloride. Where V is membrane potential, R is gas constant, T is absolute temperature, F is Faraday constant, natural logarithm, and P are permeability of the membrane to potassium, sodium, chloride, and inside outside refers uh, to the inside and outside of the cell respectively, I and O. Importance of Goldman constant in field equation. The important ions that generate the membrane potential in nerve and muscle fibers are sodium, potassium, and chloride. The voltage of membrane potential is determined by the concentration gradient of each of these ions. Relatively, the relativity of importance of each ion in determination of voltage depends on the membrane permeability of individual ion. The cation concentration from inside the membrane to outside is responsible for electronegativity inside the membrane. Due to the concentration gradient, cations diffuse to outside of the cell, leaving the non-diffusible ions inside the cell. Genesis of resting membrane potential. Resting membrane potential is the membrane potential at rest. So, resting membrane potential is electrical potential difference existing just across the plasma membrane of resting cell. So RMP is created due to the following factors. The first one is a differential permeability of the plasma membrane to different cations and anions, and differential distribution of ion across the plasma membrane due to the differential permeability and uh, Donan's effect. And then it depends on sodium. Coming to causes of resting membrane potential, first one is the permeability of membrane to potassium. Normally potassium is more inside and less outside the cell. Therefore, concentration gradient exists for potassium from inside to outside that facilitates potassium to diffuse out of the cell. At rest, permeability of the membrane to potassium is higher than any other ion. Therefore, potassium easily diffuses out of the cell through this and it is opposed by the electrical gradient. As the potassium is the major intercellular cation, its diffusion creates negativity inside the cell. The permeability of the membrane for potassium is a major cause of resting membrane potential. So here you can say, when intracellular potassium is high, it tries to move out of the cell, and then electrical gradient is produced for potassium that tries to move the potassium ion inside the cell, and thereby probably equilibrium occurs, so that is called as Nernst potential for potassium. So similarly, extracellular sodium is high and it tries to diffuse in, and then electrical gradient is produced for potassium, and this tries to enter outside, and thereby equilibrium is produced for the sodium, and that is called as Nernst equation for potassium. So relative impermeability of the membrane of resting cells to sodium. At rest, ECF sodium is more than the ICF sodium. Therefore, there is a concentration gradient for sodium from outside to inside, for which sodium diffuses into the cell. However, at rest, membrane is less permeable to sodium than the potassium. Therefore, potassium exit is not balanced by sodium entry. That is, more potassium goes out, and hence interior of the cell remains relatively negative. The third factor is permeability to anions. Exit of more cations from the cell should be accompanied by proportionate exit of anion to maintain electroneutrality. However, The exit of potassium, that is cation, is not accompanied by exit of the same amount of anions, as permeability of anions at rest is also not same as that of potassium. Therefore, there will be more negativity is going to remain inside. The another important factor is role of sodium potassium pump. The role of sodium potassium pump is to maintain RMP rather than to generate it. Sodium potassium pump also contributes to genesis of RMP, that is contribution is around minus 4 millivolts, as it is an electrogenic pump. It pumps out of 3 sodium for 2 potassium to come in. It pumps more cations out of the cell and less into the cell. Thus, less cations are taken inside, which in other words, a relatively negativity, is created inside the cell. Maintenance of resting membrane potential. Potassium diffusing out of the cell and sodium diffusing into the cell will come to halt once the concentration of gradient ceases to exist for both the ions. That does not happen, as sodium potassium ATPase helps in building up the concentration gradient. It serves to pump back the sodium that diffuses into the cell and potassium that diffuses out of the cell. So thus sodium potassium pump plays an important role in maintaining the resting membrane potential. So this is in brief about the resting membrane potential, what is resting membrane potential, and what are the factors which helps in maintenance, genesis or maintenance of resting membrane potential. Thank you.